Hello everybody, my name is Casper. I'm a PhD student from Manchester and I want to tell you about automated generation and orchestration of stream processing pipelines on FPGAs. First, I want to introduce you to this FPGA accelerator figure. As we all know, FPGAs are suited to have multiple parallel high-performance accelerators or processing elements that can be easily connected to various other devices. Often, systems using FPGA acceleration are I/O bound, meaning there are moments when a considerable amount of resources are left on the table, not doing anything while waiting for data to arrive. This presentation will go through several optimization iterations of the system architecture you see in the figure. Furthermore, we will also go through the evaluation showing where our approach succeeds. FPGAs have slow clock rates compared to other devices, and often hardware designers use wide data paths to improve throughput. Large crossbars between these modules are more expensive with wider data paths and cause congestion. Dataflows alleviate congestion as directly connected processes can exchange data directly. Additionally, fitting applications like signal processing or data analytics are easier to parallelize with deep pipelines. As a result, data flows are easier to scale. Nevertheless, most data flow architectures on FPGAs are currently static and lack flexibility. When these static pipelines have to execute work outside of the envisioned scope, they turn inefficient or inoperable. Basically, they either have unused modules that are wasting valuable resources or omit required specialized modules and have to use more general purpose processing units instead. This problem is especially apparent in systems with ad hoc requests that have data-dependent operations. Therefore, we need dynamic data flows that can adapt to various runtime conditions. Such systems are more common in distributed data flows that use virtualization and dynamic load balancing to adapt. Partial reconfiguration helps us to build dynamic data flow pipelines on a single device. For this, we need pre-built modules. We can choose the most appropriate modules to swap between batched runs if we have an extensive module library. As a constraint, the modules must be built with a predetermined interface so that the swapping would not break any existing circuits. Designing partially reconfigurable modules gives the developers several advantages. Namely, the coupled system parts are easier to maintain as they can be created in isolation and later integrated faster. Furthermore, research has shown that the tools operate faster and better with smaller designs. Most importantly, partial reconfiguration allows us to have virtually infinite resources through time multiplexing. As ad hoc requests can be arbitrarily complex, the resource requirements can easily exceed the number of resources available on a single device. Then during parsing the complex request down to execution graphs, consisting of minor operations and dependencies between them, we can also partition different nodes into different groups that get executed in different time slots. In order to enable wider topologies with many splitting and joining streams, each stream gets a unique identifier, which each module targets while passing other streams forward unaltered. Nevertheless, as we all know, partial reconfiguration is expensive and slow. Therefore, to an extent, the modules can have some flexibility. They can be programmed to target different streams and specified offsets on the wide data path. Furthermore, the functionality of the modules may also be programmed to an extent with different constant values. This programmability allows modules to be reused between the runs in different time slots. All this complexity has grown substantially and should be managed transparently, and as such, we propose a middleware responsible for operating the whole system. Operating the system includes scheduling, where the requests are parsed and partitioned to different time slots to minimize configuration and initialization costs. By configuration, we mean partial reconfiguration, and by initialization, we mean programming the modules with different memory mapped register values. We still need to address the problem of how to allocate more or fewer resources to a single operation. Usually, in partially reconfigurable systems, different modules are built within a coarse-grained region to match the interface wires. However, what if these coarse-grained module slots need more resources for the desired module? Or if the slots are then made way too big for easier core operations? With fine-grained resource partitioning, we can use a flexible amount of resources to enable resource elasticity. Resource elasticity represents the ability to change the resource allocation of a process transparently to the end user to meet varying demands. With more fine-grained partitioning in our case, modules can use multiple slots or columns. However, this requires more flexible routing, which has to be built with pre-built routing modules or blocks. Not all resource patterns appear multiple times on the device, especially on modern FPGAs. Resource patterns have to be used to match resource slots and modules to deal with this heterogeneity. In the image, the columns are partitioned based on whether they have a lookup table, block RAM, or DSP module resources. Moreover, each module in the module library has multiple variants, allowing the middleware to place modules in various locations to help reduce fragmentation. StreamProcessing modules, though, have limited buffering capabilities and offer partial functionality. For example, sorting is a blocking operation and needs to see all of the input values before being able to output any values. Therefore, in a streaming pipeline, partial sort is used to sort a smaller set of sequences which can be later merged. Stream processing, however, allows us to combine multiple modules to have a larger functional capacity. In our example, sort larger sequences. So multiple smaller modules can be split up and are easier to place. But on the other hand, we see that larger modules offer better functional capacity while taking fewer resources. This non-linear trade-off and data-dependent operations like filtering require runtime monitoring to find the optimal resource allocation. There are more opportunities to use partial reconfiguration effectively, especially if the middleware keeps parsing new requests and potentially updating the execution plan. The middleware, missing in related work, is ideal for spotting opportunities when partial reconfiguration becomes advantageous and allocates resources between operations transparently. With such dynamic management, we wonder how large the overheads are to enable this flexibility. Furthermore, is using partial reconfiguration worth it, or does using multiple static configurations give enough flexibility? We developed a system that can do image processing to check that the stream processing pipeline is functional and can handle blocks of raw pixel data that special modules can manipulate and decode. After achieving a functional stream processing system, we studied our system against a more dynamic workload, data analytics. Data analytics requires looking at table data made up of rows containing columns with different data types. Furthermore, query parsing and planning require interfacing with a database management system, such as PostgreSQL. Scheduling everyday database management system operations into multiple pipelines while placing resource-elastic modules in time and space resembles a well-studied problem, namely the resource-constrained project scheduling problem. There are various approaches to deal with this NP-hard problem. But the fastest way to schedule such problems is to use heuristics. Our heuristics contain many guidelines to place modules as densely as possible to prioritize execution plans that minimize execution times. To evaluate this approach, we first used synthetic workloads to simulate various requests representing a wide range of topologies. Moreover, as expected, the scheduling runtime was drastically minimized. But what about the quality of the resulting execution plans? As the heuristics naively target minimizing execution times, plans that minimize configuration times and reuse more modules are ignored. Consequently, while simulating workloads with small datasets, we see that configuration times dominate. However, we successfully keep execution times minimized, and we expect that with larger workloads, the execution times dominate instead. Therefore, next, we compare scheduling, execution, configuration, and initialization runtimes against the rest of the time spent on smaller processing steps. We ran SQL queries from a popular data analytics benchmark, TPCH, to evaluate against more established and larger workloads. Consequently, we see that execution does start to dominate the whole end-to-end runtimes with larger datasets. Furthermore, we crafted static pipelines using the same number of resources as the partially reconfigurable system uses. We observed that with large datasets, the dynamic system could adapt to these large datasets and allocate all resources to critical operations to gain back the time spent on reconfiguration. The advantages of a dynamic system become even more apparent when the same query is run again, but with different data. Query 19 contains a large filtering operation before the sorting operations to be able to execute a merge join. If all the records pass through the filters, the FPGA has to sort 50 times more. Here the static approach is much slower, as the runtime system allocated more resources to sorting after observing little to no filtering. The more streams are sorted and merged in a run, the less repeated I/O operations are needed, which leads to better performance as the I/O throughput is the main bottleneck. We can make the workloads even more dynamic by processing multiple queries simultaneously. Moreover, we saw that dynamic system again performed better than the static system. In conclusion, static pipelines fit small workloads and static workloads. However, when such static pipelines are also operated by a runtime system that can use partial reconfiguration to speed up the process with dynamic workloads, the end user can enjoy speed up seemingly for free. Thank you for listening. We invite you to try the system out, as everything is available on GitHub.